Until yesterday, we learned about some method to prove that graph H embedded into G. Or in other words, in G, we want to find the H. Then how can we find it? So we learned the method, which, mainly about the regularity lemma and blow lemma. So that the idea was we take G and we apply regularity lemma, then we get this epsilon regular partition. And then we make some modification, and then we also partition H accordingly and make them compatible, that epsilon regularity partition and the partition over H make compatible, and then we apply blow lemma to embed them. But one drawback of that is this regularity lemma requires this graph G to be too large. So number of vertices should be at least some very large constant, which is way more than the number of atoms in the universe. So people also have tried to find some, proof of the results without using regularity lemma. In that case, n doesn't have to be that large. So one of the ways that people used a lot is the observing method. So what observing method is, basically using the following strategy. So what we want to do is we first build an observer with some good property. So for example, let's assume that we want to find some Hamilton cycle. Then what we do is we first, build some observer so that this passage observer, it has property that every other vertices has lots of neighbors there. And then what we do is we build an approximate structure. 2P? Yeah, 2P. Approximate structure. So for example, in that case, we extend it into cycle, which covers almost all vertices but small number of leftover. And then we use the pre-built observer to convert this approximate structure into optimal structure. So in another way, there are these leftovers, and that this observer observes this problematic vertices. So in this case, because this has many neighbors here, we can find the two consecutive vertices, both are neighbor over here, and two consecutive vertices, both are neighbor here. Then we can find this Hamilton cycle. So that's the basic strategy of observing method. So of course this was too simple, so I will give you an illustration of this method by showing a theorem. So there is this conjecture by Posa, which says that if we have an n-vertex graph G, which satisfies minimum degree condition, at least 3 over 2n, then G contains a square of Hamilton cycle. So here we define Hamilton cycle as a cycle which covers all vertices in G, so which is n-vertex cycle. And then square of a graph is when you take any pair of vertices which are distance 2, then we add an edge. So in this case, we add an edge, add an edge, add an edge. Then this is square of Hamilton cycle. And then we can similarly define case power of certain graph. So actually, this is conjecture by Posa, and later Seymour conjecture that for general K, if we have a minimum degree at least that number. So if k is 2, then that's the same number as before. Then we can find the kth power of Hamilton cycle. So both conjecture was proved by Komroch-Dalcourt-Semeredi using blow-up lemma and regularity lemma. So, I mean, for all large n. And for small n, it's not fully proven yet. And what we want to prove is, we want to prove weakening of this. So 2 over 3 plus a alpha. And so it's saying that for given alpha, there is n0 such that the following holds for all n at least n0. But here, and square root of Hamilton cycle, but we want to prove this statement without using regularity lemma. So if we were to use the regularity lemma, then this n0 is tower type function, 2 to the 2 to the and many type. But since we are not going to use regularity lemma, that n0 is reasonable. I didn't compute it. I'm not quite sure, how big it should be, but something like 10 to the 100 would suffice. 10 to the something, yeah, probably like 1 digit or 2 digit number.
It should depend on alpha, right?
Yeah, of course. Yeah, of course, right. So, yeah, depending on alpha, but assuming alpha is, yeah, okay, yes, right. Anyway, so this is 20, let me see. So this method, this is proved with, without regularity lemma by Levitt, Dalcourt, Semeredi. And then the proof, so actually what they prove is without alpha. So they deleted alpha completely, and then they showed it, so it doesn't depend on alpha in their proof. So they said that minimum degree at least 2n over 3, then there is n0 such that this holds. So at that n0, it's something like 10 to the, I didn't really check that carefully, but it's not too terrible. So it's single exponential rather than tower, I think. So, but I will only present the proof with this alpha because that makes the proof quite simpler. But it still would be enough to illustrate how we can actually apply this observing method. So basic idea is as follows. So basic idea is we want to do similar thing as before. So we first build an observer, which is part of the structure. So observer also should look like this. And then for any small number of vertices, this should be able to observe that vertices. What it means is that this is square root of path. But once we add certain small number of vertices, there exists square path which consists of all these vertices with the same end vertices. So we can find a new square path which starts from here, ends from here, and pass through some of them and then come here. So we will first find such observer. And then here we want to grow this square path into square cycle, which covers almost all vertices. So, for example, we have certain other paths, and then so one of the ways here we grow some other square path, and then we connect it. And then grow some other path, we connect it. And while doing that, we want to keep it intact. We don't want to disturb it. Because this observing structure, we will do it later. But here, we might be able to say, there is this one vertex, and we kind of, include it in the middle so that the path structure might change it. But here, we don't want to disrupt it at all. And while doing that, we want to make the remaining vertices very small. But on that process, we want to use this property, right? But when this leftover vertices becomes too small, then we have no control over what it looks like. Then we cannot proceed anymore if it gets too small, but it is not small enough to actually be observed, and there could be some problem. So for overcome that, what we do is we actually take some reservoir. So we reserve some vertices at first, in a random sense that this is small enough so that later it can be observed. And then every vertex has lots of neighbors here. And then what we do is in the remaining vertices, we grow this path, square path. And then when we connect it, we use constant number of vertices in here and we connect them. We use constant number of vertices in the reservoir and we connect them. And constant number of vertices in here, we connect them. So when we grow this path inside of here, we use these vertices. And this has good property. And while doing that, we make sure that we don't use too many vertices here so that this still retain the good structure. And by doing that, we cover almost all of them. And then somehow we close it at the end, and then all the remaining vertices, we observe it to observer. So for doing that, we need to prove several facts. First, we have to build observer. Build observer with the properties that we desire. And second, we have to be able to say, connect these parts or grow this path. So we should be able to grow this square path into longer path. In either taking more vertices, or grow several things and then we connect it. And then at the end, we also have to be able to close this path into a cycle. So we should be able to connect. So, how do I write? Build an observer and connect. Yeah, we should be able to connect. And we should also build reservoir. And let's say we should also be able to extend square path. So the way to connect actually helps us to, extend the square path, but still we have to, come up with a proper way. So these are the tasks we have to do. So I will first prove a lemma regarding this connection, and then prove a lemma regarding this observer, and then I will leave this building reservoir as an exercise to you. And then in the main proof, we will use this lemma to actually prove that we can build an observer, and then we can extend it to cover almost all vertices, and then we can use this reservoir and connection to connect it into the square cycle, and then all the remaining vertices we will observe. So let's first prove a connection lemma. So when we have square of path, let's say this is AB and this is CD, then we say these are end pairs. This is one end pair, this is another end pair, and these are end pairs. Let's just call that. Then what we want to prove in this connecting lemma is that when we have AB, when you have CD, we want to be able to find the square path so this is arbitrary edge. We want to be able to find the square path starting from A, B, and ends at CD. In such a way, this is not too long. If we can do this, moreover, if we can do this through this reservoir, so if we take AB, CD, then we can find the short path through this reservoir to coming here. Then we will be able to build several paths and we can connect it in the way we want. And while doing that, we also only using small number of vertices. So then, in some sense, we can do it lots of time. So we want to prove such lemma. So that's lemma 7.2, connecting lemma. So let's say for given data, say it's less than 1 over 100, and which is positive, yeah, it is non-zero, positive. There exists, say, n0 such that the following holds. So n is still large. So if say H is on n vertex graph with minimum degree 2, at least 2 over 3 plus beta n, then for any two disjoint edges, AB and CD, there is a square path. So there is a square path. So I will omit of, so square path, square of path. I mean, yeah, it doesn't really matter. I will omit of A, B, U1, U2, U, say, what did I write here? J, C, D in H with J and more say 20 beta to the negative 2. So for any two edge A, B, we can find the square path connecting those two, which has not too long length. So how we will prove it is, we take A and B, and then we take all the common neighbor of these two. So possible next vertices. Say this is, what did I say? Say A1. And then we will find the build the A2 and A3 each level. This doesn't have to be disjoint. So some vertex might be here in both set or the other set. And we will consider this auxiliary graph between these two and bitype graph, so that each pair here has lots of vertices to go up, lots of choices to go up. So what I mean is that if we take this vertex, say G, then we can take lots of, if we fix this G, then there are lots of choices of Y that we can take so that it is an edge. And then once we fix these two, there are lots of choices in here, which is common neighbor of this. And then these two, there are, we will define it in the way this can climb up this way and climb up this way. So we will keep do that to find A1, A2, A3, A4, A5, A6. And then at certain moment, if we choose any vertex, then there are many ways to climb back on this way. So we climb back on in the way that we are keep making this square path. And then we will do same from, say, D and C. And say, so if we take this, then there are many choices, and we take, there are many choices, and we take. So we are ensuring that there are many choices because some vertex, these AIs are not disjoint. So we use G here. So we use G in the much below, and then we come up. And then at this point, there could be G. So we want to avoid using it again. But if we have many choices, then we can avoid it and we can choose other vertex instead to make all the vertices disjoint. And then what we want to do is we build up this square path and we build up this square path, and we want to connect them. So at certain point, we want to show that there exists certain vertex with a good property here. And here, there is certain vertex with a good property here. And with that good property, we want to connect them. Then this gives us our square path from AB to CD. So that's how we will do. So let's define the level AI and the auxiliary bipartite graph between AI, which is G.
So are those points with good property different from that reservoir that you mentioned?
Oh, could you say again?
So you said you...
Okay. Yeah. So we prove this lemma, and then we just take the reservoir which satisfies this property. Then we can use this connection lemma to the reservoir so that we can connect. So this is the lemma that, give us this property, and then we, build a reservoir with a certain, appropriate property that's compatible with this lemma. So this is actually, we will actually use this lemma to the reservoir at the later. So let's just do for the AB first. CD, we will do the accordingly later. So for A, B, we consider the sets A0, A1, A2, and bipartite graph. GI on bipartition, say AI minus 1 and AI. So maybe some picture would help. So we have A, we have B. So, and let's say this is A0, A1. In A1, what we want to take is just the common neighbor of A and B. And so G1 is a star at is, let's say, okay, complete bipartite graph. Between A0 and A1. So which is just the star between P and here. And then let's say this A1 has size at least say 1/3 plus beta times n, because this vertex has minimum degree 2/3 plus beta times n. This has 2/3 plus beta times n, so it should overlap at least this much. Yeah, there could be 2 in the beta, but it doesn't really matter. But we know that it has linear size. And we let A prime to be or common neighbor of B and X here. So how we will build A1, A2, A3 is we will first build, say, A, I prime, which give us, so let's say A, I minus 1, and A, I minus 2. So if we have certain square path up until to here, the next time we should be able to take lots of vertices here. We should be able to, there should be lots of choices here, right? And then there should be also lots of choices here. So this vertex have an effect on choices here and here. So we want to make sure that both of them has a lot of choices. Yeah? So we first take A prime, which vertex has a G. If we choose later Y appropriately, then we have a lot of choices of, say, X. Then we will put it in A prime first. So we are not guaranteed yet there are many choices of Y. But if we choose the right vertex Y, then we have lots of choices of X. If G satisfies a certain property, then we will put it in A prime first. And then once we obtain A prime, we now see that for this G, whether there are many choices of Y or not. And then if there are not so many choices of Y, then we will take it out. We will kick out. And then left over is our A. So we will first consider about this first, and then we collect all the G such that this choice of X is large once we choose Y appropriately. And then see how many that appropriate choices are there for G. And then if there are not so many, then we will kick it out. So at this point, if we look at this, so that's right. So in here, we want to first make sure that there are many choices of here, and then we consider here. But this is a bit special because in 2 levels above, there are only one choice. So A2 is slightly differently defined than the later one. But the philosophy is the same. So we take all the vertices so that which has X. So for this X, so X and B has a common neighbor here. That means for this, if we choose X appropriately, then we can climb up. So that's A prime. And say G prime 2 with a bipartite graph that encodes the information about which pair can be choose. Which pair we can choose, say X1 and X and Y, which belong to A1 and A prime 2, so that the Y is common neighbor of B and X. So if there is triangle here, then this is okay, and this vertex is in A prime 2, and this is in G prime 2. Yes. And what we will do is, we let A2 be the ones that are in this A2, which has lots of choice to go above. Here, lots of choice is, say, beta square. So from here, if we are here, then we want to choose this vertex. And there are at least beta square and choices. Then we leave, and then the rest of them we throw it away. And G2 is just the induced subgraph of this G prime 2 in A1 and A2. So if we start from, say, here, then we can choose at least beta square and choices of this next vertex. And then once we choose next vertex, then we can go to B and we can go to A. So is it clear? So how we define this? And then we will define in the same manner, but now now the 2 level above was 1 vertex, so it was a bit simpler, but now it's less simple. So assume.
Do we know that A2 is non-empty?
Give me a moment. Yes, because let me see. Yes, because so for each, say, y, so this is, which one did I say y? Okay, let's say this was g. Yeah. For each y in A1, what's the degree of y in G prime 1? So here to G prime 1, how did it define? It's common neighbor of B. So it's, if these two vertex has common neighbor, then it sends an edge in G prime, right? So we know that this has degree at least 2/3 plus beta, and this has degree at least 2/3 of beta. So this vertex sends at least 1/3 and plus beta neighbor. Right? So all of the vertices have degree this much. So A prime 2, even if it's as large as n vertices, if it sends this much edges in here, and this has size also at least this, so there are at least 1/9 n squared edges between. So there should be at least certain large number of vertices send at least this many edges from below to up.
Yeah, but do we know whether A2 prime is not too big?
It's at most n.
I understand.
Yeah, size. So the number of edges between them is at least 1/9 n squared, because there are 1/3 n vertices sending each 1/3 n edges. Right? So if there are, say, n vertices, and say all of them is smaller than beta square n edges degree, then the degree sum is too low. So actually we can show that this is at least as big as 1/3 n. So A2 has at least as big as yeah. So assume that we have defined A0 to say A sub J. J and this J are different J, so yeah, the J in the statement is different from this J. But this is arbitrary J we chose. And define G1 to Gj with J at least 2. And we will construct AJ plus 1 and GJ plus 1. So the situation is like this. So say A2 has side also LS3N. So we have defined up until to AJ minus 1 AJ. So this is GJ. Now we want to define next level. Again, the idea is similar. So now what we want to check is we want to add this G here if there is certain Y, so that if we choose this, then there are many choices of X here. So that's the first step to define A prime. And then we want to make sure that there are also many choices of Y. And if not, we will delete some vertices and we get A. So to encode this information for fixed Y, so for this G, and if we fix Y, whether there is many choices, so to encode that information, we consider that this graph. So for each Y in AJ, let PYJ be a graph with its edge set P sub YJ is between X and G if X is a neighbor of Y. So there is this edge which belongs to GJ. So which not only belong to, H, it belongs to GJ so that we can later go up again. And G is arbitrary vertex. So because we haven't defined the vertices here yet, so anything is still candidate. And this G is in common neighbor of Y and X. So this forms a triangle. So if for this Y, if we choose G and Y together, then we can go up to X, then we add an edge between X and Y, G and X.
Sorry, what is G?
This one?
No, G. The graph.
G sub J?
No, I mean.
Okay, H. Sorry. Yeah, H. Yeah, in the printout it's all, yeah, again G, sorry. Yeah, that's H. So let's say A prime J plus 1 with all G such that there exists Y. So as I mentioned before, for this G, there exists Y so that we have many choices of X. Such that in this graph, B sub Yj, this G has degree, say, beta to the 4 times n. So some linear number. But, so this beta to the 4 and beta to the 2 is chosen in this way because we want one of them to be smaller than the other so that later we can prove certain good property. So here we use beta to the 4, and later when we delete these vertices, we want to make sure that so there are at least beta square choices of going here and beta fourth choices of going here in this way. But anyway, so we define it this way, and then G prime J plus 1 to be number of edges in YG, which should be an edge in H. So Y is in AJ, and D of P Y sub J is at least beta square n. So what it means? So what it means is that so this is now collection of vertices G, such that there exists one Y, so that if we choose this Y, G together, then there are many choices of X we can extend. That we put it here. And then we add this edge between Y and G if this together has many choices here. So that's the graph G prime. So there is H G prime means that once we choose both of them, then there are at least beta to the 4 times n choices of X so that we can keep proceed. So, and then again, so we can keep proceed. So that means that we have our desired property, except that for this fixed G, the number of Y might be still not big. There exists one choice, but one choice is not enough. So we take that we delete some vertices, which is in this A prime, which has too few choices of Y. So out of these vertices, if in this G prime J plus 1, the vertex G has 2 small choices we delete. So at least beta square n choices, then we keep. And Gj plus 1 is, just induce subgraph between Aj and Aj plus 1. So we delete some vertices. And then now in this Aj plus 1, if we have G, then there are many choices of Y. And then once we choose both of them, then there are still many choices of go up. And also keep go up. So this defines this level. And again, this is not disjoint. So some vertex could belong to several levels. So now what we want to do is we want to choose some vertex. Yeah. What we want to do is we want to do this in here and do the same way in C, D, C, J, C1, C2, and CJ, CJ plus 1. Do it here, and then somehow we want to connect those two. And when we connect it, what would be useful for us is that, let's say if we have this vertex, which sends a lot of neighbor to up. Say this has size at least 1 over 3n. Then what would happen is that if we take any neighbor of this vertex, any neighbor in H, it could be outside, it doesn't matter. So any neighbor, then this has degree at least 2, 3 over n plus some beta n. This has that much degree, and this has size at least 1/3 n. So neighbor of this and this should overlap. So this sends lots of neighbor there. Then our definition says that all of them are actually in here. So any neighbor of that is always in here. And these edges are all in G prime. And then this has size large. In the same way, this vertex also has large size. And what we can do is that we take arbitrary common neighborhood of these two, which exists because this has degree at least 2/3 n, and this has at least 2/3 n. And this has, again, lots of neighbors here, which is at least 1/3 n plus beta, and 1/3 n plus beta n. And between these two, there should be an edge. Because if you take arbitrary vertex here, then that has degree at least 2/3 n plus beta n, and this has size 1/3 n. So there should be overlap. There is an edge, and that looks this way. And then we take this as our common neighbor. This is our common neighbor. So this is part of our square path. And then from here, we can keep climb up. And from here, we can keep climb up. And while climbing up, we avoid using these vertices. And when we choose these vertices, we make sure that they are all disjoint from A, B, C, D. Then we can complete this task. So what we want is we want to find this vertex which sends lots of neighbors upward. To show that, how we will show is that we will show that vertices here sends lots of vertices downward. Then either one of two things happen. The next level is much bigger than, not much bigger, but quite bigger than before. In that case, I mean, every vertex could send small number of vertices upward. Otherwise, there should exist some vertex sending lots of vertices upward. But the former case doesn't happen too many times. If it expands, it's okay at first, but it expands again, expands again, expands again. There are limits. You can never get more than n vertices. That means there should be at some point, not too later. So we can bound the number of vertices participating. So we keep do this, and at certain moment, not too far from now, not too far in the future, we will get a vertex which sends vertex upward. Then we can connect. So that's our strategy. So for that, we first prove that the vertices send every vertex sends the edges downward quite a lot. That's the first thing we want to show to, that purpose. So that's claim 5. So for all J at least 2 and Y in A sub J, we have in the graph G prime of J plus 1 Y, its degree in G prime is at least 1/3 plus beta times n. Of course, we have this G, so it would be better if we just prove it with the degree in G. But, let's just prove for G prime first, and then we use it later to, bound this expansion in graph G. So G prime was the original graph before deleting this, vertices in A prime, right? And the definition of A prime and G are all listed here. So let S be the number of vertices G. So our situation is again like, so we have AJ minus 1, AJ, this is Y, this is A prime J plus 1. So let us be the number of vertices G with Y, together with Y, the degree in this graph P to the J sub U is less than beta 4 to the N. What it means is that for this Y and this G, so say it could be outside. So this G, this and this together, there are not many choices of edge. If we connect Y and G, there are not many vertices in X that we can choose. Then these are not counted. So these are the bad vertices which are not counted by this G prime. So G prime, we add edge between Y and G if this together guarantees many choices of y, many choices of x. So we add h between y and g in g prime only if there are many choices of x guaranteed. But if that's not guaranteed, then we count them as an n. S, then exactly n minus s is the degree of this y in g prime. Then, so this graph, so for fixed y, we add h between x and g if they together, give us a triangle and we can, climb up. Then we can analyze the number of edges in this graph. So upper bound is that for all bad vertices S, it's at most, so for this bad vertex G, for this fixed Y, we add h between x and g in this graph B if, they form this triangle, but this is bad because the choices of x is small. How small? At most beta to the 4 times n. And there are s many such vertices. So that's the upper bound for contribution of these bad vertices. And then all good vertices, there are n minus s good vertices. They contribute the, let me write it in better way, the d sub gj is between these two. So they contribute at most this many. So for good g, there could be maximum number of x we can choose is actually x and y should be connected by this gj, right? Otherwise, we don't take it x. So this is maximum possible. So this is upper bound for the, say, number of edges in b to the jy. And then which is actually equal to the, if we take all the x which are connected with y in this g sub j, and we take its common neighbor. Every time we have this common neighbor, we add this in, no, not this. We add this into this g prime. That's the definition of g prime. G prime encodes the information that x and g are eligible if through y. So, common degree of y and x. And this is that for fixed y, it has degree at least 2/3 plus beta, and this vertex has at least 2/3 plus beta. So this is always at least 2/3, 1/3 plus 2 beta, n. So this is degree of g sub gy, so which is the choices of x, times 1/3 plus, say, 2 beta n. And we have this inequality. We divide it by this, and then we move around. Then we get n minus s is at least, we divide it, this goes away. 1/3 plus 2 beta n minus beta to the 4 and s over degree of gj y. And g, remember, we have this g. Initially we had g prime and a prime, but we deleted the vertex which has degree less than beta square n. This y is survived one. That means from down to up, it sends at least beta square n edges. So this is at least beta square n. So this is beta 4. So it cancels out at most 2 beta here, but still something left. So this is actually smaller than something like beta square s, which is smaller than beta square n. So subtracting doesn't hurt much. So this is at least 1/3 plus beta n. So this was 2 beta, and this is smaller than, say, beta square n. Then we get this. And n minus s was exactly the degree. So we have this claim. So now we show that from above, it sends lots of edges, at least in G prime. And then now we want to show that either, because of this, either this level expands or there is some vertex which sends lots of edges above. Let's say such vertex which sends lots of edges above has heavy edges. Let's keep this definition, and I will just write this again. So let's say we say Y is a J heavy if Y is in AJ and degree of YJ, Y in GJ is at least n over 3. So claim 6. There exists J, which is at most say 5 times beta to the negative 2, such that AJ contains a J heavy vertex. So in the claim, it says that we can find many J heavy vertices, which is true, but in our purpose, only one J heavy vertex is enough. So let's just prove this. So suppose not. If that's not true, then what we will show is that the level keep expands. And because it cannot expand too much, we will get a contradiction. Because what it says is that it keep expands up until to 5 times beta square, beta to negative 2 square much. But that's impossible if this happens. We will show that AJ is bigger than 1 plus beta square AJ minus 1 or J and most beta 5 times beta to the negative 2. This cannot happen because we already know that say A2 is at least 1 over 3n. And if that happens, 1 over 3n times, every time we expand 1 plus beta square time, and 5 beta to the negative 2 time, then this is, we know that the 1 plus x to the x, and x is smaller, 1 over x goes to e, the natural log. Yeah, in our class we have natural log, which makes everything fancy anyway. So then we will reach this much, but that's impossible. That's bigger than n. So if we show that this, then we can obtain a contradiction. So choose a smallest J such that, say, this is 7.1. 7.1 does not hold. Then that means up until now it always expanded. And J is the first time it doesn't expand. Then by the choice, we know that A sub J minus 1 is at least n over 3. It's at least say A sub 2, which is at least n over 3. Then, because of claim 5, what we know is that the vertices in up sends many edges. That's claim 5. So if we consider this Gi, Gj, then it's actually for all the vertices above. So a sub j minus 1, a sub j, and here is a sub a prime j minus aj. So we know that all the vertices here sends edges, which is d, g prime, j, y many. And then we have to subtract the number of edges that we have deleted. So let's say this way, these edges are not counted in G. These are in G prime, but not in G. So these are in G and G prime both. So this count all the edges in G prime, and then we subtract, say, G in A prime J minus AJ, and degree of G prime J plus 1 G. So we add all these edges and we subtract. Then that gives us this number of edges in G. And how much is that? How many is that? So this claim 5 says that every vertex here sends many edges. How many edges? 1/3 plus beta n many edges. And the size, the number of vertices in this. And then here, this was kicked out because this sent 2 little edges above. That was the reason. How little? So, no, not here. Yeah, here. Because it sends less than beta square n edges. That's the reason why it kicked out. So this is at most beta square n. And how many vertices have kicked out? At most n. So this is the lower bound. Then we have this lower bound. On the other hand, if we consider its upper bound, then we assume that there are no heavy vertices downside. So for all vertices in A sub j, the down part, we add its degree, then it's at most 1/3 n, because we said that no vertex is heavy. So it's 1/3 n, and how many such vertices? A sub j. So this is lower bound and this is upper bound. Then what we get is 1/3 n A sub j is bigger than 1/3 plus beta n A sub j minus 1 minus beta square n square. Then, then we know that this, okay, so, and we delete it, 1 plus 3 beta, and what have we deleted? Okay, and this 3, so we have this, right?
Why is the index j plus 1 not j in the sum?
Yeah, you are correct. J, yeah. Yeah, we don't have j plus 1. We have j, yep. This is correct. Did I write it here? Yeah, so maybe what I wrote here is also, one directional is also wrong. So j. Yeah. Yeah, right. Yeah, thank you. So we have this. And then because this has size at least n over 3, this part is much smaller than here. And beta is 1/100, less than 1/100. That's what we assume. So only 2 beta times this is 2 beta, at least 2 beta times n times 3, which is far bigger than this, so which is at least 1 plus, say beta. And what we wanted to show that was actually square, okay, aj minus 1. So this is a contradiction because we chose j, which is smallest, which doesn't expand. 7.1 doesn't hold. But now we just show that it holds if there is no heavy vortex. So there must be a heavy vortex with the index not too big. So now we are quite close to prove what we want. So again, we want to do as before. So we have this heavy vortex. We have this heavy vortex. And we take its common neighbor, say u. And then we consider its neighbor in down part. And then we know that this has large size because every neighbor of it has lots of neighbors inside of here. This is quite large. So this is essentially entire neighborhood of this y sub a. And this is, say, y sub b, y sub c. Then this y sub a has its entire neighborhood, which has at least 2/3 n plus beta n size, 2/3 n plus beta n size. And this has degree also 2/3 n plus beta size, so its common degree, common neighbor is at least 1/3 n plus beta and 1/3 n plus beta n. So there should be an edge. So that connects these two, and then we can climb back up, and while going up, we avoid using same vertex again, then we can connect. So, by claim 6, there exists j of 1, which is m mod 5 beta square, and sets a0, a1, a, and g1, g2, and so on, such that y sub a is in a sub j1 is j sub 1 heavy. Similarly, with D and C, we can find sets C sub 0 and say G, H, F, say F1, F2, such that the Y sub C is C sub J2 is J2 heavy. Then we choose a vertex U, which is outside of A, B, C, D, in common neighbor of Y, A, Y, C, just like this. Has minimum degree of H is at least 2/3 plus beta times n. Every vertex G whose neighbor of YA has at least beta n neighbors in n of G sub J1 YA, which means that here, so every vertex in here has at least beta n neighbors here. So by the definition, so G is also a neighbor of YA in G prime J1 plus 1. So actually this level, we don't have to consider G. As long as we choose this, and this is already fixed. then we can go up. G prime ensures that we can go up, right? G is because we take G because once we fix this, we are able to choose this in lots of ways. But in this case, we already choose this, so when we choose this, we don't really need to, choose this level again. So we only consider G prime. Then all the neighbor of Y is in here. Hence, in G prime, say 1 plus 1. So in this graph, YA has size at least 2n over 3. So likewise for Y3, Y sub C, there exists an H GA, GC between neighborhood of, YJ in this graph, YA, and neighborhood of G prime, F prime, say 2 plus 1 in YC. Then we are done as then YA, CA, U, CC, YC forms a square path. So, and then by using the definition of G, J, G, say I, AI, and C, FI, and CI, we can extend it into a square path A, P, and to this YA, GA, U, CC, YC, and CD with length at most, say 20 beta to the negative 2. Because the heavy vertex here occurs before 5 times beta square, beta to the negative 2 square. So this also occurs before 5 times beta to the negative 2 square, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 more vertices. So this is an upper bound. So this proves this connecting lemma. We said that whatever graph satisfies this, if we have two edges, we can connect it by square path which has not too long length. Next lemma we want to prove is observing lemma. So now we need to build an observer which can observe any small number of vertices. So what we need is observer itself should be a square path. And then whatever other small number of vertices we take, there is another square path which covers all the vertices in the observer and then the given small set, so that its end pairs are same as before. So for given beta, say m of 100, there is n0 such that the following holds for n at least n0. So if say G is on n vertex graph with minimum degree at least 2/3 plus beta n, then there exists a square path P sub A in G with, say, at most, so if beta to 10n vertices. So we also want that this observer is not too big, because we want to take it at the beginning and then we want to pull it out. And after pulling it out, we want the remaining graph still should satisfy good property, that the minimum degree condition. So, moreover, such that for every subset U, which is outside of this observer, which has size at most, say, small, beta to be 20, and there exists a square path P sub AU in G with the vertex set of P sub AU is exactly the vertex set of P sub A union U, and P sub AU has the same end pairs as PA. So we want to prove this. So, to prove that, we need to be able to come up with a way to observe one vertex. So when can we observe one vertex into a square path? So we will use this structure. Let's say we have this square path. If we have B, say it's adjacent to all 5 of them, then we have A, B, C, D, A, B, X, C, D. So A, B, and C, D are starting and ending. And if it's adjacent to all of them, then we can just write A, B, X, B, C, D. Then this is an edge, this is an edge, this is an edge, this is an edge. There is additional edges, but it becomes, again, square path with the same end vertices and this observed V. So we say that a 5-tuple X, A, B, C, D observes V if all 5 vertices are neighbors of V, and A, B, C, D are neighbors of X, and A, B, C, D forms an edge, forms a path. So that's exactly what it said. X is adjacent to everything. A, B, C, D itself forms a path. So if this holds, then we say that 5-tuple observed V, that 5 ordered tuple. And then how we will do it, we will find a bunch of 5 tuples that observes vertices. So how we will prove it for each vertex B? We show that there are, so this is all collection of 5 tuples. All collection of 5 tuples. And we show that this B, for this B, there are many 5 tuples that observe this specific vertex B. And then another D prime, there are also many 5 tuples that observe this. And there are many n such vertices. And then out of these 5 tuples, we choose certain 5 tuples randomly, so that the number of 5 tuples here are not too large. And then we show that because for each one of them there are many, in this random sample, there should be substantial number of 5 tuples here that observe this, and here also that observe this. So for any vertex, there are certain number of 5 tuples that observed here. If we show that, then we take virtue of 5 tuples, and then let's say all the vertices outside here has at least 10 observers, 10 tuples observing here, 10 tuples observing here, 10 tuples observing here, 10 tuples observing here. And then each of them looks like A, B, X, C, D. A, B, X, C, D. Square path. And then if some of them overlap, we delete. And some of them doesn't even form path or something, then we also delete. And then rest of them we use the connecting lemma to connect into square path. Then we get square path. And then as soon as, say, in this case, as soon as there are 10 vertices, then for this, we choose one observer. For this, we choose one observer which has not been chosen yet. So every vertex has, 10 tuples that observe this. Then if there are less than 10 vertices, then that can be easily observed. So by this approach, we can prove this observing lemma. So for that, let's just count the number of 5 tuples that observing specific vertex B for given B. So which is claim. So time is coming to an end, but allow me a bit more minute, because I was planning to cover a bit more, but I couldn't. So for this G, for this vertex in G, we can show that there are at least, say, 2 to the beta to the 5 and to the 5 many 5 tuples observing this specific vertex B. So we specify this structure of 5 tuples. We have X and A, B, C, D. All should lie inside of neighborhood of B. So for given B, so how many choices can we choose for X? We have at least 2/3 plus beta n choices of X. We can choose X among its neighbor. And for given, we fix one of them. For given X, for fixed X, consider U, which is common neighbor of B and X. Then this U has size at least 1/3 plus 2 beta n. From there, we can choose this A, B, C, D. And by the minimum degree condition, since minimum degree of G is at least 2/3 plus beta n, and this U has size 1/3 plus 2 beta n, so this we have U, an entire graph. If we have vertex, and even if it's, it has as many neighbors outside in its tab, it has at most 2/3 minus beta minus 2 beta n. So it should have at least 2 beta n neighbors inside. 3 beta n? Yeah, 3 beta n. 3 beta.
To write it as when you remove A, B, and C.
Oh, could you say again? How could you say again? Oh, okay. Remove.
You're not removing anything right now.
No, we haven't choose ABCD yet. So we are just saying that, I'm just saying that we have that this G, induced graph, induced subgraph of G, induced by G, has a minimum degree L3 beta n. So we can choose A by size any vertex in U, and then B as a neighbor of A, which has 3 beta n choices. And C, how many choices? Neighbor of B by 3 beta n choices. And D also by 3 beta n choices.
-1, -2.
Yeah, -1, -3, okay. Yes, that is correct. Let's just, that is correct. Yeah. And we just multiply all together, then we get 2/3 plus beta n size of U plus 3 beta n minus 3 to the 3. Then we get 2 beta to the 5 and to the 5. So we prove this claim.
So is this tuple ordered tuple?
Yeah, ordered tuple. So we prove this claim. So for each B, there are many. How do I do more? So we prove that for each B, we have many ordered 5 tuples that observe this. And let's say, okay, let's prove one more claim so that we wouldn't go over time in the afternoon. Yeah, so let curly A sub B with a family of 5 tuples which observes B. Then what we showed is that it has size at least 2 times beta to the 5 times n to the 5 for all vertices B. Then, as I mentioned before, what we want to do is we want to take a collection of 5 tuples. So there exists a family curly F of at most, so it doesn't contain too much, 2 times beta to the 14 and disjoint 5 tuples. So pairwise disjoint 5 tuples. So as I explained before, we are aiming to find these tuples, and then we will connect it by using connecting lemma into a square path. So we want them to be pairwise disjoint. Such that for every vertex B, we have the number of 5 tuples in F which observes B is at least beta to the 20n. So for each vertex, there are many observers, many 5 tuples that observes it. So, how do we do it is we first we select a family, say F prime of 5 tuples of vertices at random by each n minus 1, n minus 2, n minus 3, n minus 4, 5 tuples independently with probability exactly beta to the 14 times n to the negative 4. So this is all 5 tuples. We don't care whether it's observed something or not. It doesn't matter. Any 5 tuple, we flip a coin, and then which comes up with head with this small probability, then we include it. Otherwise, we don't include it. Then, by using Cherenkov inequality, it is easy to show that it is left as an exercise. With probability 0.99, we can show that this F prime has size almost twice times beta to the 14 times n. Because this is the probability, and there are roughly n to the 5 many tuples. If you multiply, then you get expectation, which is beta to the 14 times n. So it's almost twice of expectation with high probability. And for each B, we have this observer, the number of 5 tuples in F which observe this B is at least beta to the negative 19n. Because, what have we said? For each B, we have at least this many 5 tuples observing that specific vertex B. And then the probability that we choose each of them is beta to the 14 times n to the negative 4. So in expectation, we get 2 times beta to the 19th and many tuples are chosen which can observe the vertex B. And this is half of its expectation. So by Cherenkov, we know that this is very concentrated on its expectation. So this happens with high probability. And there are n such vertices by union bound. Even if you multiply n on the probability, it's negligible. So with high probability, both of these property holds. And once we have these both properties, still there are a bit problem because it's not yet pairwise disjoint. And we can actually take care of that. So furthermore, the expected number of intersecting pairs of 5 tuples in F is at most n to the 5 times 5 times 5 times n to the 4 times beta to the 14 times n to the 4 square. Because you fix x, a, b, c, d, one tuple by n to the 5 many choices. And then you choose one of them which will intersect with other. So there are 5 choices. And then in new pair, we designate a coordinate which will use the same thing, which is another 5. And we define, and we choose the other 4, which is n to the 4. And then the probability that both of them are here is this probability square. Then how much is it? This is 25 beta to the 28n, which is really small. So by Markov inequality, this F3 holds with probability at least half. (50 times beta to the 28 and pairs of intersecting 5 tuples in F prime. Then what do? We take it and if some pairs intersect, then we delete one of them. While doing that, we might pick out some tuples that observe certain vertex. But that effect is negligible. So even if we subtract this from here, so this is beta to the 19, this is beta to the 28, and beta is smaller than 1 over 100. So this is less than half of this. So we can make sure that so we delete all the intersecting pairs from F prime, and then in F prime there could be some tuples that doesn't observe anything. We also delete it. Because in that case this is not affected. Because that tuple doesn't observe anything, so this is still same. So after that, we still get this is at least beta to the 19n minus this 50 beta to the 28n at least beta to the 20n. And also I forgot to mention that so this holds with probability 99% and this holds with probability 50%. So with the union bound, there exists a choice that all three holds. We choose it and then we delete it and then we do this. This procedure. So we are almost done. Now we consider this F, which is a F1, F2 to F sub say F, small f, which satisfies this claim. And for each, say, fi plus 1 and fi plus 2, so what we do is we use the connecting lemma. The connecting lemma says that if we specify two h, then we can connect it by path. But while doing that, only property that we need is this. So what we do is in this G, we delete all these vertices. We take it out. Then how many vertices do we take out? Negligible. It's much less than beta over 2n. So remaining vertices still forms a graph with minimum degree at least 2/3 plus beta over 2 times n. And then we add, say, this is AB and this is CD. Then we add these 4 vertices back. So we deleted all these vertices in this F, and then we put these 4 vertices back. Then in there, we have this AB and CD, and here we have moved out F1, F2, F3. Then we apply connecting lemma there. Then there is a square path connecting this, which doesn't use many vertices. So we can connect it. After connecting it, now these used vertices are also kicked out. And then we put this vertex back. And then we connect it. And then, because here what we said is the size of where is the claim? So we said that this F is at most 2 times beta to the 14n. And every time we connect it, the number of vertices we use is at most 20 beta to the -2 vertices. So b to the 14, and we do it this many times, that the number of vertices we have to move away is at most beta to the 10n. So we can keep doing this. After taking that out, still the remaining vertices has minimum degree at least 2 over 3 plus beta over 2n. So we can do this to build a square path so that it contains these square paths as a consecutive vertices, and which can absorb the vertex. So it's actually easy to check that this actually satisfies the property here, because the number of vertices in here is at most this times 5 plus the vertices that we have at, and which is less than beta to the 10 times n. We can easily check. And then, because each vertex, there are at least beta to the 20 and tuples that absorbs this V. Once we are given at most beta to the 20 vertices U, then we can observe it. So we have this path, and in each part we have F1, F2. Then for certain vertex B, we choose one of them, and then we can put B here without disrupting anything. And next vertex, we don't use it, but we can use it here, and we can keep putting in. So that proves this lemma. I will not write the end bit rigorously, because we are a bit late for lunchtime. So we proved this connecting lemma and observing lemma, which are useful tool for proving this Posas theorem, approximate version of Posas theorem that we will prove. And then there is reservoir lemma, and then the actual proof of how we use this. So we will do that in the afternoon. Yes, thank you.